everybody. Today, Julianna Tymoczko is going to tell us about webs and quantum representations.
Thank you. So this represents a really long collection, long collaboration with Heather Russell, now at the University of Richmond, as well as a lot of different students. And I mean, I think if I had to pull out a single theme that's like been a through line in all of my research, it's been graphs with certain kinds of labelings that both are determined by algebraic conditions, and then in turn determine some kind of algebraic structure with some kind of meaning in some other area. I have a really mathematically inclined cat who I'm sure you will see a little longer. So that's sort of where webs are sitting. They are a certain kind of labeled graph that talks about representations. So I'm going to focus a little bit on, I'm going to try to focus on sort of combinatorial aspects. So these sort of three closely related combinatorial objects and different kinds of correspondences between them. So one of those is the stranded webs. Another one is balanced Yamanuchi words, which have a lot of equivalent combinatorial formulations, some of which you'll see. And then a third is multicolored non-crossing matchings. So I try to avoid acronyms, but non-crossing matchings is a mouthful and long. So you'll see NCMs all over the place. And specifically, what I'm going to aim for, which will likely take too long, so defining webs and strandings from the sort of big picture and algebraic perspective, then sort of back up a little bit to talk about words and multicolored non-crossing matchings, and talk about some combinatorial aspects of words and multicolored matchings, and then talk about ordering stranded webs. And then I'll back up once again and talk a little bit about geometry and Springer fibers and some other orders for Springer fibers. So that's the basic plan. And here's the overall idea about what webs are. So they're a way of taking graphs and encoding representations of sort of quantum SLN representations. So the idea is that each web is some kind of invariant vector. And then there are scheme theoretic relations on the webs that are sort of encoding algebraic relations on the corresponding representations. So it's an invariant vector in the sense that there's some matrix group like object somewhere that works on this vector, and in some meaningful representation theory way, doesn't change the vector. And then, kind of elementary linear algebra, there could be lots of different ways of writing a vector. You could write it as the sum of two other vectors or the difference of two other vectors. And so they're like graph theoretic processes that allow you to encode this. And the whole reason to do this is because linear algebra is hard and representations are icky, and graphs are beautiful and allow us to also visualize and sort of have human intuition about what kinds of structures the representations share. So that's the big picture. And more technically, so there is a sort of category, the SLN spider category, that takes this representation theory of the associated quantum group to SLN and sort of moves it. So there's like a functor that takes one category and represents it with graphs. So in this category, the morphisms are called the SLN webs. Here's my sort of schematic picture. You'll see versions of this coming repeatedly during the talk. So web edges have some kind of weight. They are like labeled with a number that depends on the choice of n. It also is a directed graph. The edge decorations at the boundary are sort of indicating what vector space, so what vector space your input and output of this morphism are contained in. And then the all of the stuff between the boundary, top and bottom boundary, that interior of the web, is describing some kind of specific homomorphism between two vector spaces. So here's sort of a specific example. I will speak a little bit vaguely, and then in a few slides, explain why I'm speaking a little bit vaguely. Well, in two ways. If you've got a web where all of the vertices lie on one axis, that indicates that you have some kind of invariant action. So this is a web vector that is invariant under the action of the quantum group for SLN. And these two different ways of thinking about it, either as a morphism or an invariant vector, they're on some level algebraically equivalent. You can take one of the boundaries and like slide it up, and that'll involve changing your essentially sort of thinking about either a homomorphism or a dual object. So you don't really need to worry about that. So that's like, so I think about them as web vectors, as invariant web vectors, mostly for convenience. So one reason why I'm speaking a little bit vaguely is because there's a ton of different conventions for how we draw webs, and then how specifically you construct the web vectors out of the webs. And so if you were trying to say something sort of meaningful on a graph theoretic level, then you want to pick one of these conventions and use that particular convention. So here is a picture with some of the different people. On that top left, the Countess, Chemnitzer, Morrison picture on the top left of the screen. I'm just going to sort of flag that for your attention because we will return to that and say a couple words about that. The one on the bottom left from Greg Cooperberg. So that one you can also take a little gander at, and we will also return to that description. All right, so what a web is you've got a whole bunch of web graphs. They have relations that are encoding a statement of here are two vector spaces that are actually, they appear different, but they are actually the same according to some algebraic operations. So you have those web relations, and if you take an equivalence class of graphs under those relations, that's what a web is. So for SL3, here are the relations. They look like game theoretic kind of things. So you could just erase any closed loops, and then you have to add some sort of coefficient to your vector. If you have like a strand with a like little loop stuck into it, you can erase that loop, turn it just into a strand, and again, you're gonna have to scale by something. And then if you see these kinds of squares here, you could kind of erase one pair of parallel edges from the square, or erase the other pair of parallel edges, and you just add up. That's sort of like a thing you do in the middle of the graph in two different ways. You get two different graphs out of that, add those up, and that's the sort of vector, the corresponding vector for that web relation. I drew these, well, my collaborator made the nice slides, this particular one, but I'm showing you SL3 because part of the story is that SL3 is well understood. SL2 is like completely understood. And then things get really mysterious in a way that we'll talk about soon afterwards. So this is super manageable. SL4 relations take up an entire page, well, and SLN. So here's what I just said. To compute with webs, we have to understand how these relations work, which graphs are equivalent. And so sort of when you think about a web, what are all possible ways of writing it in terms of graphs? And n equals 2, n equals 3, this is easy, but easy. And then there's a sort of computational trick that allows us to handle n equals 4. So Colin Hagemeyer, a PhD student of Cooperberg's, does that. And then for larger n, there's a couple of different constructions. Countess Chemnitzer Morrison's is sort of the most robust setup, and it's the only place in the literature where somebody proves a complete set of relations. So actually kind of tells you what the web vectors are, sort of step by step. But let's see, I will probably complain a couple other times in a sort of philosophical point of view. But one issue is that their webs don't actually just directly generalize the webs for n less than or equal to 4. So these SL3 web relations that I'm showing you are, I think, like reproduced essentially like Cooperberg. Cooperberg did a lot of early work on this. And that sort of first strain of thinking about webs didn't put so there's sort of like implicitly the number 1 is sitting above all of these edges, which is great. When Countess, Chemnitzer, and Morrison sort of write things down and prove some sort of, it's more than a folk theorem, things that I think people believed, you know, there should be some way of writing a relation down. So they actually write it down and prove it carefully. But they add tags to their edges to keep track of whether you have, whether sort of on each edge you are thinking about a fundamental representation or its dual. These are sort of a representation theory distinction that you can basically just avoid because of small dimension issues for SL2 and SL3, but that becomes more and more important the larger n gets. And the issue with that is that, like, there are no tags here. So the sort of things we would like to say about webs from a graph theoretic point of view don't really entirely make sense anymore in the Countess, Chemnitzer, Morrison framework. So, oh, good. Here's another thing that just always bugged me about the CKM web construction. So they are not in any sense obviously invariants of the plane graphs. So what I mean by this is that whatever we want a web to be, the first thing that it is a planar graph that has been embedded in a particular way in the plane. We don't care, like, so however you embed it in the plane, you should get the same vector out at the end of the day. So we don't like care how it's been embedded, but we're going to want to embed it in one particular way. And CKM webs, all their local relations care very much whether you put a straight line between two vertices or whether you have it like wobble up and down a whole bunch of times. And then they can prove that in fact it does not matter how you draw that, but that is like not evident in their construction. And it is built into webs for SL2 and SL3. It is built into definitions of webs that come without a full set of relations like Fontaine's. So kind of bringing us back for a second, I'd like to analyze representations, and I'd like to answer questions, specific questions like, give me some good bases for web space. If you give me a web, how can I tell if it's one of these basis vectors? If you give me a random vector in web space, how can I write it in terms of a particular basis? And somehow, like, really behind all of these, how does the graph theory, the sort of combinatorics of this question, allow me to simplify and do concrete representation theory calculations. So all of these are hard to do when n is greater than or equal to 4, especially. So because of time, I'm going to skim through this and just try to say some concrete things about what I would understand a web as. So first, it is a plane graph. So I've got a planar graph, I've embedded it. I'm going to be thinking about my webs as invariant vectors rather than functions. So I've got one boundary, and so that is going to look like I've got an axis, and I've got univalent vertices along this axis on the boundary. Any internal vertex is trivalent. Every edge has an orientation, and it has an element of 1 through n minus 1. So it's labeled mod n, essentially. And then at each trivalent vertex, I have a sort of conservation of flow condition. So the sum of the incoming edge weights minus the sum of the outgoing edge weights is divisible by n, or congruent to 0 mod n. So here's a picture of an SL5 web. There it is. So each of the boundary vertices just has one edge. Each edge can be in or out. And they're at the, exactly why I wanted this guy. All right, so like, here's a vertex on the top left. It's got 2 edges coming in, labeled 2 and 1, and 1 edge going out, that's labeled 3. So 2 plus 1 minus 3 is 0. And let's see, yeah, great. Whereas this vertex here in the middle has 1 edge coming in, labeled 1, 2 edges going out, labeled 4 plus 2, 1 minus 6 is minus 5, which is 0 mod 5. So this satisfies our conditions. I'm checking that everywhere. Okay. If you care about concrete representation theory, for my tastes, I've already talked too much about representation theory, but if you care, the web vectors themselves lie in some tensor product of either a quantum wedge product or a dual of this quantum wedge product. So that is why I am going to start labeling edges, not just with numbers. I'm going to refine this labeling with essentially binary vectors. So the basis vectors for any sort of wedge product are just take a subset of the basis vectors for the underlying vector space, or their duals. So I can just sort of remember which basis vectors show up in a wedge, and that tells me a sort of basis vector for the overall fundamental representation. So one piece, so with Heather, we've developed a formalization of webs that's kind of interest, especially if you want to do representation theory. And that, so that sort of proves a set of relations for Fontaine's construction and eliminates this issue with the CKM graphs. And I'm not right here calling it a theorem, I'm just calling it an idea. But at each trivalent vertex, really what we're saying is, here's an invariant vector in a threefold tensor product with one vector coming from each edge, roughly something like this. And then we can combine these vectors using a contraction process where like only certain compatible terms are going to persist. So you can sort of think of this as, if I have 2 different wedge products and then I wedge them together, that's going to vanish if there's any repeated basis vectors. And it will only survive if you've got sort of exactly complementary, or if you've got complementary labelings. So So we do a sort of contraction process. And then we get sort of two things from this. So one, we're going to get some sort of like overall invariant vector by doing this. But then two, we can sort of see that that web vector is going to decompose into specific terms. And these terms are going to come from a statement about which basis vectors are on, so which invariant, so which basis vectors in the wedge product are associated to each of the edges. So here in red, one possible term in this overall web vector is coming from this kind of binary labeling that you see at the bottom in red. And then, sorry, there's the subset. I will generally just use binary strings to sort of remember sort of how many of my basis vectors are wedged together. So then, more precisely, binary labeling of a web is a choice of an n-bit binary string for each edge, so that the string, so that I'm going to give you a conservation of flow at each interior vertex, but binary string version. So the string on an edge that's labeled k has exactly k1s. The sum of the incoming binary strings minus the sum of the outgoing binary strings is constant, meaning the all ones vector, you can scale it by some integer and get the sum of incoming minus outgoing. So see if we could find a good, yeah, here's a nice example. So right here in the middle, I have nothing incoming, and then outgoing, I have 0001, 0100, and 1010. So minus the all ones vector, which is constant. All right, so then what a web vector is a way of, it's adding all binary labelings on a web graph, and the coefficient is coming from this sort of local contributions at each trivalent vertex and contraction. This would be the conventional way of thinking about it. Now let's talk about strandings and change this convention. So given a binary labeling, an IJ stranding is constructing the following kind of directed graph. So for each edge in the web graph and binary label on that string, I'm going to sort of direct the edge UV if the ith bit is 1 and the jth bit is 0, or direct it the opposite direction if the ith bit is 0 and the jth bit is 1. And I'm not going to include any here, either both bits are 0 or both bits are 1. So here is sort of one version of how we can how we would construct for when I equals 1 and 3, we get these kinds of edges. So the edge 2, 4 has, so the edge 2, 4 labeled 2, 4 has nothing in the stranding. 1, 3 has an edge pointing up. 1, 4 has an edge pointing up. 2, 3 has an edge pointing down, and so on. And then what we generally do is we draw all of the I plus 1 strandings together, and we use different colors to distinguish them. So I'm going to always be using blue for the 1, 2 strandings, red for the 2, 3 strandings, green for the 3, 4 strandings. So 1, 0, 1, 0 has a blue edge pointing up. That's my 1, 2, a red edge pointing down. It's 2, 3, and a green edge pointing up again. That's 3, 4. So on the one hand, I've told you kind of just a local process at each edge and each vertex of this graph representing this sort of representation. But here are some sort of global properties about it. So anytime that a strand enters an internal web vertex, it's also going to leave that vertex. There's also at most one strand going through any vertex. So it's never going to get trapped at an internal vertex. The strand will not get trapped at an internal vertex, and you can't have multiple multiple strands of the same type or same color coming into a vertex. And so what this means is that each part of the IJ stranding is like they form a directed non-crossing matching on a subset of the web's boundary vertices. So here on the left, a web that one we saw a little bit earlier. Here on the right is sort of one particular strand, one particular stranding wrapping through this graph. So this is the green 3-4 stranding. And you can see that if you sort of ignore all of the vertices, you've got like a sort of green thing with another green thing underneath it. And they don't cross, they don't intersect at any vertices. It is possible to have closed cycles in the interior of the web. All right, so then furthermore, every web edge carries at least one I, I plus one strand. So this sort of collection of I plus one strands itself creates what we call a multicolored non-crossing matching that covers the entire web. So a non-crossing matching is a matching represented usually as arcs from boundary vertices. And what it means to be non-crossing is like literally none of the arcs cross. What it means to be a multicolored non-crossing matching is that you've given each of these arcs a color, and within each color, arcs cannot cross, but arcs of different colors are allowed to cross. So on the bottom right here, we've drawn the multicolored non-crossing matching, and you can see red is crossing both green and blue. That's allowed because red doesn't cross red, nor does green cross green, and so on. In a multicolored non-crossing matching, you can also have sort of red arcs and blue arcs meeting at a vertex, at a boundary vertex, which you would typically not have in a standard ordinary non-crossing matching. So the sort of punchline here is, well, it's maybe one other thing that's like not immediately obvious, but not huge. So these I plus one strands, so they're actually creating a multicolored directed non-crossing matching that covers the entire web. They also, just knowing the information of the I plus one strands allows you to infer uniquely all of the IJ strandings, just coming from, there's essentially the same simple transpositions generate all transpositions. So there's a stranding analog of that. So like if you look on the bottom right, this multicolored non-crossing matching, so on the one hand, you have lost some amount of structure from the web graph on the left, but on the other hand, you have gained a certain amount of global structure, right? So these strandings, which we apparently construct locally, are in fact these sort of global objects on the webs. So going into this idea a little bit more depth. So these terms in the web vector, these multicolor directed non-crossing matchings, they are on some level measuring how complex the web is. So let me go back here. What this picture is saying is, in order, so if you see on the left-hand side, all I'm doing is saying, I'm going to pick which vectors are going to appear in a particular term of the invariant vector. And here I'm sort of asking, does this term show up in a web vector? And on the right-hand side, we're saying, well, there's actually only one way to direct a non-crossing matching that fits between these vertices, and it has a certain amount of nested depth. So these integers on the faces are telling you that they are telling you sort of how many arcs are lying above each region. So the only kinds of webs that can support this stranding, or equivalently, the only sort of vectors that can have this term show up, are web graphs that have enough depth to match up with these numbers that you see on these faces. So in addition, we can use strandings to create labelings. So also to to create specific binary labelings, we can sort of understand again, global structure. And we can, I will show you more pictures of ways in which the combinatorics of non-crossing matchings is sort of appearing in sort of fundamental ways inside the webs. All right, so let me shift to a more combinatorial, some more combinatorial statements. So a word in the alphabet 1 through n is balanced if it has the same number of instances of each letter in the alphabet. So one of these is balanced, the other one isn't. So the thing on the right has different number of 2s as 1s, so that's the one that is not balanced. The thing on the left, they're all out of order, but there are exactly 2 of each number 1 through 4. And word is Yamanouchi if for each I, the first I letters of the word have at least as many instances of 1 as 2, and 2 is 3, and 3 is 4, and so on and so forth. So one of these is Yamanouchi, the other is not. I'm going to pause for a second. Let's see. Moving left to right. Definitely looks like it's working on the left, but it definitely looks like the condition fails on the right-hand side. So the first letter is a 3, and there's no 1s, no 2s. So it is not true that there are at least as many 1s before the first 3 as 2s, or 2s as 3s, and so on. Balanced Yamanouchi words are, as you know, classical objects. The symmetric group also acts on these words by permuting positions. So like think of it as you can exchange the I and I plus first position. This might or might not change the word itself. So here, acting on the 4th and 5th position, on the top, we're going to exchange 3 and 2. In the bottom, they happen to be the same, so there's no action there. So we can get a poset on the balanced words using reverse lexicographic order. So each of these covering relations in the poset corresponds to a descent in the word. I'm just going to look at balanced Yamanouchi words to make it easier. Here's the picture that I am talking about. If we go down to the very bottom example, so we're starting with 1, 2, 3, 4, 1, 2, 3, 4, and this first exchange is just flipping the 4, 1 and the 1, 4. So the things that are more in alphabetical order are on the top. And so every time that we can do a flip and make the number more into alphabetical order, then we move up. So we have up at the top, after doing a bunch of flips, we've got it like fully in lexicographic order up at the top. Okay. So back to our multicolored non-crossing matchings. For historical and bad slide reasons, sorry, I started drawing my arcs above the bound border instead of below. So back to our matchings, we can actually construct multicolored non-crossing matchings from balanced Yamanouchi words. The idea is you go through your balanced Yamanouchi word. Every time you see an I, look to the left for an I-1 that has not yet been matched, match them, erase, and then repeat. So we're going to just keep matching in the, sort of impose the non-crossing condition and start matching repeatedly. So matchings also have a property called nesting and unnesting, kind of self-evident. They are nested if one arc is on top of the other. They are unnested if they are not on top of each other. And we can do so this is both a property of a matching. How many arcs are nested? Is this arc nested or not? And also an operation that you can do on a matching. So you can take some nested things and then unnest them. Or a little bit more complicated, you could start nesting. So we're going to do this operation on non-crossing matchings and even multicolored non-crossing matchings. So as long as there's nothing of the same color nested in between, then we can unnest nested arcs. And that's what I have in this particular picture right here. So you can see at the very top, there are 2 blue arcs, 2 red arcs, 2 green arcs. If I go down the middle edge, which I've labeled red, I've labeled that red to indicate that I'm going to take those 2 red arcs and unnest them. So the multicolored non-crossing matching that I just underlined has the same blue arcs, the same relative position of blue arcs, same relative position of green arcs, but the red arcs just became unnested. I could also unnest just the blue arcs or unnest just the green arcs, whatever I want to do. And keep moving through this process. Down at the very bottom, I have sort of fully unnested everything. So it has just unnested blue arcs, just unnested red arcs, just unnested green arcs. And perhaps you've noticed, well, first thing perhaps you've noticed, these posets are actually the same. So those 2 sort of things that I just showed you, the first poset is coming from permuting positions on the word. The second poset is permuting sort of values. So the 1 and 3, the actual letters rather than the positions. But then back to what we were saying before, what's happening with strandings is these strandings are sort of, strandings are telling us about the, so strandings are sort of combining these 2 combinatorial models and kind of showing them both at the same time. So the boundary word is sort of ordering these certain vectors, and the matching is telling you which boundary points are connected by certain relations in the vectors. And so the directed paths through this web graph is telling us what the stranding is doing. And so this actually is going to now give us more operations on these underlying graphs. So just like we can act by transpositions on all parts of this labeling. That's going to flip the direction of a strand of type I plus 1. And then it may also sort of stretch strands of type I minus 1 and I plus 1 out of position, sort of really changing the global position. So the sort of global structure can change really very dramatically with this sort of local flipping. So for instance, on this left-hand side, I have a red strand that right up here. So there's a red strand. And if I want to flip it, right now it is going counterclockwise. So over in the right-hand side, that same red strand has been flipped to go clockwise instead. And when I did that, I had to rearrange the green and blue strands in order to still satisfy the stranding, the sort of binary labeling condition on every edge. So the sort of radically the way these paths are moving through the graphs, but is doing it systematically and trackably. So we have a conjecture about this, that any graph, understanding this in an appropriate place, there's like some details about what I'd like to, a couple of details, but I am not putting in here. So if a graph can be stranded clockwise by a particular multicolored non-crossing matching, then it can also be stranded by any matching lower in the poset. And furthermore, we conjecture that you can move back and forth between these strandings by flipping individual strands. And I'm gonna skip most of the geometry and just show you one additional picture. So part of how we noticed that strandings and that there was this sort of global structure on web graphs is from a sort of geometric object, Springer fibers. So Springer fibers are a kind of subvariety that show up in representation of symmetric groups. They're a subvariety of the flag variety. They're related to Schubert calculus or akin to Schubert calculus. I'm not going to talk about any of this sort of geometry, but happy to talk about it afterwards if anyone's interested. Arise in representation theory, but they also have a sort of interesting paving. So they can be sort of, the geometry can be pulled apart in a way that's like a CW complex, but worse, in the sense that it only takes pieces of a cell rather than, so Springer fibers are cut into affine cells that have topologically poor qualities. So sort of your classic way of decomposing an object is into a cell whose closure is a union of smaller dimensional cells. And so in the best kinds of combinatorial geometry, like Schubert calculus, you have Schubert cells. And if you take the closure of a Schubert cell, you are just actually taking the union of a bunch of smaller dimensional Schubert cells. And that recovers Bruhat order. So like Schubert cell corresponds to a permutation, and the closure is all of the permutations that are lower in Bruhat order. So that does not appear, it can't happen for Springer fibers because they're sort of not containing full pieces of the cell. They're sort of both an element coming from a partition and an element coming from the cell itself. So I was going through some statements about pavings and saying that they're hard to understand. So if we focus just on the top dimensional pieces, people know that they are connected to, that they are indexed by standard Young tableau, which are the same as balanced Yamanouchi words. People know that there's some kind of relations that are described by these simple transpositions. And I'm drawing a poset that looks a little like what I had earlier. So the theorem here is that the two-row Springer fibers are naturally indexed by these multicolored non-crossing matchings. And when we say naturally indexed in this context, here I'm giving you both colors of arcs and a variable, because if I want to actually give sort of local coordinate systems for my underlying algebraic variety, it's related to exactly how these different multicolored arcs are nested one over another. So the entries in the matrix are these sort of variables, and you see them first, second, third, depending on where the arcs are related. So these matchings are SL2 webs. And the next theorem that we realized is that these SL2 webs, if you want to find closures of Springer fiber cells, you can just unnest the arcs, and that sort of the same reading rules that allow you to reconstruct the variety happen after, like, you can still use them to reconstruct which part of the cell is being included. So up at the top, we have a nested pair. This is the big top dimensional cell. So this is sort of a free piece. If you move to the right, the cut B arrow, we've got sort of two pieces of the top arc and the same variable on both. And this is actually just a slice of the top dimensional cell that is contained in the closure of another cell. So this is a sort of statement about a partial order. So the nesting partial order on these non-crossing matchings is the closure order for a certain variety, the cells of these two-row Springer fibers. So does it extend to three-row Springer fibers? Well, to do this, we would actually need another color of our non-crossing matchings. So we would need multicolored non-crossing matchings, Yamanouchi words on three symbols, 1, 2, 3, and in fact, we would want to somehow combine so these arcs, in order to sort of keep staying inside of the correct dimension of the variety, we want to create just interior trivalent vertices, which we can do through this kind of resolution process on the bottom. So in this case, yes, we can sort of do it, but in the linear algebra, you can see a third color, the purple color, showing up in some of the entries. So again, going back to depths, the purple color, that third color, is this depth map. This is sort of, so this depth color is independently identifiable as a third color, multicolored non-crossing matching. So if I erase the red and teal edges and just look at purple, then every region of this graph that was labeled 1 is going to be labeled 1 by purple. Every place that's labeled 2 has 2 purple edges above it. every place that's labeled 3 has 3 purple edges above it. So it's sort of like just recovering the depths. And so the kind of, okay, so what this is furthermore encoding is the following. To get all of the entries in the Springer cell for n equals 3, we need to look at the web represented. I squared it off for convenience. So the Springer cells are giving us this web, whereas the simplest, the sort of basis web, is this web right here. So I've squared things off, but wherever you see there's certain places with trivalent vertices, this is still representing a web. So your Springer cells can be read fully directly from certain non-reduced webs. Once you put strandings and just follow along where the strands are going and keep track of when regions are being split by strands of various colors. So we get a fully algorithmic way from strandings on particular webs of describing these entries and just parameterizing this algebraic variety. So here would be the takeaway from this whole piece. Springer fibers and the sort of permutations that you get from Springer fibers they also recover web graphs as well as multicolored non-crossing matchings. The way that the multicolored non-crossing matching goes through this web graph, so this stranding is encoding the entries of the Springer fiber cell and answering sort of deeply mysterious geometric questions. And these sort of same questions that sort of arise in the quantum representation world about nesting and depth are in the Springer fiber geometry world, encoding elements of this sort of, calling it like a bundle structure, but sort of when you're picking up dependence in one entry of the matrix on earlier variables in the cell. And then this is like the super optimistic statement. I mean, all of this appears to be generalizable in many different ways, but the calculations do get very complicated. And I will stop at this point. So thank you for the invitation. This has been supported by many different funding mechanisms, including NSF and AWM MERP and the Budapest semesters in mathematics, which has a really phenomenal visiting mathematician program and many students. Thank you.
Thank you, Julianna, so much for your talk. Are there any questions for Julianna?
I have a question.
Yes.
So your diagrams involving the non crossing paths reminded me of the Temperley-Lieb algebra, and it which is this classical algebra used to study the representation theory of UQSL SL2 and UQSL2 and whatnot. Are we looking at with these webs? Are we looking at some kind of generalization of the Temperley-Lieb algebra?
That is exactly it. Yes, and so SL2 webs are the Temperley-Lieb algebra, and so I think the sort of classical construction of SL3 webs, right? So you with these interior vertices, like it becomes very different feeling immediately, but in a sense I would say like the strandings, the idea of a multicolored non-crossing matching overlaid onto the graph is sort of explaining, right? Like these sort of smaller copies of the temporally lead algebra inside the larger SLN webs, right? Yes, 100%. Thank you.
Okay. I have another question. So, SL2, SL3, SLN gets a lot of press. What about the affine SL2? So UQ SL2 hat. Is there a web theory attached to that algebra?
Boy, that is a great question. I thought you were going to say other Lie types. Other Lie types I can answer better. Kuperberg has a little bit, and then Stroppel and Wilbert and other people have some constructions there. Affine, I don't know, but I would look at Stroppel and the people that she works with to see. I don't know. And I mean, I guess for what it's worth, I think you are also right that variations of 2 are significantly more manageable than increasing the number 2.
So that is one argument in favor of looking, sticking to UQSL2 hat and whatnot. So do I understand correctly that the present state of the art in the theories is about the finite dimensional Lie algebras as opposed to getting into the affine case or worse?
Yes.
Okay. On a few slides back, you had these sequences involving zeros, ones, and minus ones, which reminded me of alternating sign matrices, where every row and column involves a sequence of zeros, ones, and minus ones in this exactly in this alternating way. Now, here we have a row that doesn't correspond to a row in an alternating sign matrix, but because we see 2 minus ones adjacent. If you insist that the ones and minus ones alternate, does that give you anything particularly nice in this context?
This is a good question. I've never thought about that. And yeah, I guess I've never thought about it. So these numbers, the -1, 0, and 1s, are coming from Kovanov-Kuperberg's, so these are the same 1, 2, 3 of the balanced Yamanuchi word, but Kovanov-Kuperberg sort of used -1, 0, 1. But I guess what they're doing in the sort of matrix of the Springer fiber is they're sort of indicating that there's certain regions that either are kind of getting more deep, right? Like there's some interaction between two different SL2, two different SL2 things are either getting more deep, less deep, or staying the same. So a shocking, gosh, maybe. Yeah, really, maybe. And cool. Yeah, that seems actually kind of reasonable that there is some sort of alternating sign matrix structure And that would be sort of fundamentally coming from these matrices, the underlying Springer fiber matrices, or like a different sort of encoding of some of this structure inside the matrix. Huh.
Well, that was just wild speculation on my part.
Yeah, well, I would say it, yeah, wild speculation, but kind of maybe cool.
At one point, you showed the post set involving the Yamanouchi words. Um, yeah, is is that always going to be a distributive lattice? That post set?
So remind me, distributive, there's one top, one bottom. What is a defining feature of a distributive lattice?
Right. You start with a smaller post set, and then you construct the distributive lattice post set by taking all the lower ideals and
Yeah,
order them by inclusion.
I believe that, yes, it should be.
It looks, this one here
Yes, yeah,
looks
I
like
think it should be, yeah, it should be a distributive lattice, yeah. Because you can sort of erase any number of letters and restrict down to the post set that you would get on a smaller alphabet.
Yeah. Well, very interesting.
Thank you.